Hello everyone, welcome back to the latest lecture session. So as we were discussing in the last session, in this session we are going to talk about estimating what's going to happen to a particular system. The system can be a lake, a river, it can be your city and so on and so forth. Right here we can be estimating variables like BOD and COD, which we are discussing or were discussing until the last session, or we can be estimating any other parameters, let's say, right? For example, there is a leak of, let's say, a particular toxic compound in this particular room, let's say, and this room is closed on all sides. There is no input, no output, but a toxic compound has been released here. And let's say, it reacts with oxygen in the air and can become a more benign compound, let's say, that's relatively less toxic or not toxic. So I can model or figure out, let's say, if I have the relevant rate constant for that particular reaction, how much time it will take to for the room to become safe, let's say, right? So I'm just estimating the time required for that particular variable to decrease to a particular value, right? So again, here we are estimating relevant models here, right, or using relevant models to estimate variables. So again, here I guess we were talking about estimating BOD, but what we are going to discuss now, which is mass balance, right? It's mass balance is going to be applicable to you, during the class. In general, people talk about petty formulas and ask you to regurgitate them and keep reusing them in this class. But again, that's going to be pretty boring. I'm certainly sure for the student and even for the instructor. So I'm going to do away with it. So we are going to look at the fundamentals. So obviously, everyone might not need this level of knowledge, let's say. But again, it's always much better than mugging up formulas without knowing what it is that we are doing and why we are doing, right? So again, we are talking about estimating parameters. In this case, let's say BOD, let's say. For example, I have a lake and Nainital Lake. This is certainly true of Lake Nainital. You should visit it, if and when you end up in Roorkee. So let's say, during rainfall in the upper reaches, the relevant stream with considerable human population around, it brings down a lot of organic matter into the lake. And please note that you have built up areas all around the lake. So typically outlet is over a dam here, if I can say so. I guess I should not call it a dam, let's say, right? So what's going to happen to this particular organic content in this lake now? Or I can also try to estimate what's the concentration of the organic content or the DO in this particular point of the lake where the city is drawing its water supply from, right? So different models, different way to estimate, but again the key aspect is obviously mass balance. Mass is always balanced now, right? So we want to develop a model to explain and more importantly, I guess, predict the behavior of a system, right? And how do we do that? The key aspect is that the matter or matter must follow the laws of physics, right? I think you are the expert here. It can never be destroyed, let's say, right? It just changes form, right? So that's why we are obviously looking at mass balance here. But here I am talking about systems. So compounds coming in, compounds leaving out of the system, undergoing reactions, let's say. So what am I concerned with? I am concerned with mass coming in, mass going out, and reactions occurring in the system, let's say, that can affect the concentration of the system. So mass coming in is an important aspect, mass going out, and so on and so forth. So here, there are some aspects that we need to look at. So we are going to apply mass balance, obviously. So let's look at what mass balance is about. So there are some specific, not steps, let's say, guidelines. So let's just have an overview and then dig deeper. Again, as I mentioned, we could be mugging up formulas here, and I guess that would certainly not tickle your buds out here, right? And I don't want you to, take it too easy too, right? So let's see what we have. We need to also test you in the exams, right? If and when we have the exam this semester. So again, what do we have? We are going to have to choose a control volume. In the previous example, the control volume would have been the lake, right? I want to have my lake as the control volume. And then I need to, choose the variable or the substance upon which I am conducting the mass balance or the budget, let's say, right? So, in the earlier example, I wanted to conduct it on the organic compound. In the example of the toxic compound in this room, I want to conduct the mass balance on the compound or the toxic compound, and the control volume would have been the room, right. So, that is something to keep in mind. And then what else? So, again, is it for sulfur, SO2 or so on and so forth, because the reactions are specific to the relevant compound, let us see, right. And then all the imports and exports as in add sources and subtract sinks as in organic compound coming into the what do we say, control volume, and let us say leaving the control volume, let us see, right, due to runoff all the water coming into the lake and water being or water overflowing from the lake outlet or water being extracted from the lakes, right, mass coming in and mass going out of the system, right. And also if there are any reactions occurring, we need to also take that into account, let us say, right. So, accumulation is what we are talking about is equal to input minus output, right, and rate of accumulation will be equal to obviously rate of input minus rate of output, right. So, that is something to keep in mind. So, here I have different examples out here though, because we are going to get a bit more technical out here. I guess if I am not wrong, we have either an industry out here or the wastewater treatment plant here, right, that is leaving their waste into the river, let us say, discharging their waste into the river. So, here they discharge it into the middle of the stream with diffusers at the bottom, so that it gets mixed well, but because of the type of flow, I guess streamline flow that we have out here, right, it's we see little to no mixing out here, turbulence is pretty less. So, let us say here what is happening now, how is the compound being transported from here to here, right. My compound is let us say at time t is equal to 0, my compound this thing is here, right, let us say compound A, and the same compound A reaches here at time equal to let us say 1 minute, right. So, that is fine, but what is this phenomena that is leading to transport of the contaminant from one place to the other? This contaminant A is being transported from point X to point Y because of the transport of the what is it now, net transport of the fluid in one direction. The fluid is obviously the river water here. Net transport of the fluid in a particular direction is transporting my compound from one point in space to the other point in space. So, this we call advection, right. This I am going to call it as advection. Again, transport along with the fluid which is flowing or which has flow in net flow in one direction, let us see, right. So, that is what we have, advection. So, examples for advection, let us say wind blowing up a pile of leaves, but again that is not a great example. I think this is a great example for advection now, right. But again wind taking pollutant from one city to other, that is also an example of advection, but there are other aspects out there. But what do you see out here? Here again you have another wastewater treatment plant. This is again, I am not sure how good the contrast is, but you see again via diffusers they are releasing the waste in the center of this particular canal, and you see the waste coming out here. And we know that, I guess, from the shape of this plume, I am saying plume, right, this is the plume, right, this is the plume. We see that the net what do we say, fluid flow is in this direction, right. So, I do know that advection is occurring because let us say compound release here is being transported along with the fluid flow in one particular direction. There is net fluid flow in one direction. So, we know that this is advection, but looks like the compound is also going about in this direction, let us see. But I know that there is no net fluid flow in this direction laterally, right. But why is it the plume width increases, let us see, right. How are the pollutants traveling laterally now, right. So, that is because of diffusion, right. For example, here this is an empty room and I am staring at this camera here. Well, that is why I have the zombie face out here, right. So, let us say if you were sitting on the backmost row, let us say 8 rows down, and I open a bottle of scent here. And please note that this room is entirely closed and no fans, nothing, because I guess we need to give you a pretty good, what do we say, quality audio output, let's see, right. So again, I open my scent bottle here, and after some time the person sitting at the farthest point in this room can sense it. What does it mean when I say that he can sense the scent? It means that the relatively volatile compound which is in the scent bottle has traveled from here to the point in space where that particular person is sitting, right. And but there is no fluid flow in this particular room, right. It's completely still. But how is it that you have this volatile compound being transported from one location to the other? It's by diffusion, let's say. And what drives it? It's due to concentration gradient, let's say. Whenever there is a what do we say, difference in concentration or concentration gradient, the system moves in such a way, concentration gradient moves in such a way that there is going to be what do we say, the chemical potential is going to be relatively lowest of the relevant system, let's say, right. Again, what do we say, concentration gradient or difference in concentration will drive this particular molecular diffusion. So this is molecular diffusion, let's say, the example that I just gave you, right. Over time the compounds are going to reach there, and let's say after a certain, what do we say, point in time or a certain time, the whole the concentration of this particular volatile scent compound will be the same all across the room, let's say, right. So at that point we will have steady state again. So what do we have out here? We discussed molecular diffusion, but now let's say I turn on the fans, right. There is no net flow in any direction, net flow of the fluid in any particular direction, but it's not still either, right. The conditions inside the room are not still either, right. So that's turbulent, the conditions are turbulent. So in that case, again, obviously if I open the scent bottle, the time it takes for the volatile compound to travel from my particular hand or the bottle to the student sitting in the last bench is going to be relatively lesser than the case if than the current case, let's say, when I have no fans on, let's say when it's completely still, right. So the other case would be turbulent diffusion. So turbulent diffusion, right. So these are again different ways of transport. One transport was advection. Here you see little to no diffusion, let's say, but here you do see some diffusion. So relatively more turbulent conditions, I would believe. Typically turbulent diffusion is about 100 times faster than molecular diffusion, right. So that's something to keep in mind. So let's move on. I guess let's say now I want to calculate, I know the waste that's coming in out here, the concentration of the waste here, concentration. I know the flow rate of that waste. Concentration is mass per volume, and flow is what now? Volume per time, right. Flow rate, let's say, is volume per time, and similarly I know the, what do we say, background concentration here and flow rate of the river. So let's say this is, let's say, Haridwar, let's say, right, and let's say Rishikesh is somewhere way down out here, not Rishikesh, pardon me, Roorkee is somewhere out here, and let's say this what is it now, Sitkul, which we talked about earlier, that industrial zone is discharging their waste into the lake, and I want to calculate the concentration of the compound in Roorkee now, right. So how do I do that? I need to obviously apply a model across the relevant river, right, and then estimate, if I know the concentration here in Haridwar, what will be the concentration in Roorkee, right. So for that again I need a control volume, which is my river. I need the mass flux coming in, mass flux going out. I need to know the reactions occurring in the system. Typically I use this term for, not term, symbol for what do we say, reactions occurring, but that can sometimes be misleading. Please do take a note of that, right. So how do I calculate the BOD at Roorkee, let's say, right. So these are the challenges and such. So again, what do we see out here? Here we have point source, but then due to advection it's traveling in this direction, but due to diffusion the pollutant is also getting diluted in this direction, right. So, only from here do we have a completely mixed plume, but here it is a partially mixed plume. But again, diffusion and advection, two different forms of transport. Why is that necessary? We will see that. So, here let us say we were talking about, we are going to talk about, let us say air pollution too, and we have this particular chimney out here, let us say, right, and that is the wind is blowing in this direction. So, there is a net flow of fluid in this particular direction. So, that is why this particular transport is called advection, and you are going to have turbulent conditions in your atmosphere due to, what do we say, air, what do we say, traveling upwards or such, because of hot surface of the land. So, here you are going to have turbulent conditions, that is why you see that you have transport in this direction too. This is due to turbulent diffusion, right. So, advection taking it in this way, turbulent diffusion in this way, and obviously gravity deposition too. So, for example, if I know the concentration here in Haridwar, what is the concentration of this particular pollutant in Roorkee, or if I know the concentration of this particulate matter near Delhi or national capital region, what will be the concentration in Roorkee? I can calculate that, right. So, let us keep going. So, again more data, I guess, or graphs to help understand advection and diffusion. So, in y axis I have concentration and here advection. So, at time t1, let us say, if this is the profile concentration. So, if it is only advection, so obviously it is going to look like this at time t2. But with what is it now, diffusion, what is going to happen if at time t1 it is like this, and after certain time you see that this is the profile, I guess. So, obviously if it is advection plus diffusion, different what do we say, profile now, right. So, that is something obvious. Now, you see the effects of advection here, right. Again, I think I have a better graph. Yes, this is a better graph, not a better graph, an actual set of data here. So, here I have area of a tracer cloud in which bromide concentration is greater than 1 milligram per liter, right. I think this is from the US, the data that I have is from the US, I should have given the reference. So, that is my bad. So, again and here within this particular area they are studying the tracer, let us see, okay. And anything else? Okay. So, we have the monitoring wells and so on and so forth, that is not necessary right now. Okay. So, from the contour levels you can see 13.8, 7, so on and so forth. You can see that the water is flowing in this direction, or the groundwater, this is with respect to groundwater, right, higher to lower, right. So, water is flowing in this direction, yes, we know that. And then we have this injection well where this bromide, let us say, has been injected at a certain concentration into the through the injection well into the groundwater. So, after 33 days, if it was only advection, it should have been something like this somewhere out here, and after 347 days somewhere out here, and after 461 days somewhere out here, let us see, right. But as you see, it is not only advection as in travel along with the net fluid flow in one direction. We know that groundwater is flowing in this direction, but you see that it is not retaining the same shape. Let us see what is happening out here. As you see, due to diffusion in this particular direction, the plume's shape, which is in this manner, has changed, right. Again, why is it, what is happening? Or now here you have typically diffusion out here, right. So, that is what you see. But if I look at it from the side, well, I guess this is because of the aquifer. We do still see some diffusion, but not not much in this direction. We see the effect of diffusion being more pronounced in this direction, right. So, firstly, how has it gone from here 0 to 25 to 100 to 200 via advection, flow along with the groundwater, and how is it increasing in size, right. This is via diffusion now, right. Again, this is what happens, for example, we have a lab on campus. I mean, I am not going to give out the name yet, because I guess I will get into trouble. So, let us say they dump their waste, and now we have a chemical waste or hazardous waste program. So, they dump their waste into the ground now, right, and what is going to happen to the waste that's been dumped into the ground now, the toxic compounds, right, initially nearer the particular place or source, and then over time the shape is going to increase, the compound is going to get adsorbed onto the soil, and that is going to act as a reservoir, and as you see wider areas are going to be contaminated. So, and again please note that this shape is for one time release, and if it was what do we say continuous source, obviously the plume shape of the or the contaminated plume will be much bigger, and all the people drawing water from this area will be suffering the adverse effects of that, I mean of ingestion of that particular compound. Again, I guess you understand some of the aspects that I am discussing here and the reason why we need to look at this, right. Again, we face this everywhere. So, again, how do I predict this or how do I understand this now, right? It is not a bigger model, it is a smaller model that I need to look at. So, I need to know the mass flux. Flux is I guess with respect to mass here, mass per area per time, right. Flux coming in, mass flux going out of that particular compound. So, that is why we need to choose a compound upon which we are applying the mass balance. And also I need to understand or frame my control volume, let us see, right. This is my control volume out here, and then any reactions occurring within this particular control volume, right. So, what do we have out here? The fundamental mass balance of what do we see equation, the accumulation term change in mass with time is nothing but mass coming in minus the mass going out and any sources or sinks within the control volume, right. So, how can I express this? I have dou C by dou T or dC by dt, pardon me, and the del operator with respect to the flux, right, is equal to plus or minus sources or sinks. J is the flux, del operator, right, del product here, and sources or sinks, let us see. So, what do we have here? C is the concentration of the compound that you are applying the mass balance upon. T is obviously the time with respect to time, change in concentration of the compound with time, and J is the flux, as I mentioned, mass per area per time, right. S is source or sinks. Del operator here in this context, I guess again del product, right, is nothing but dou by dou x, dou by dou y, dou by dou z of J, right. So, that is what we have out here, right. So, again this flux, what is it due to? We, as we discussed earlier, flux is due to both advection and due to diffusion, right. Advection it's U, I guess U times concentration. Flux, I think it is diffusion coefficient minus, because it is due to the concentration gradient, and del product of C. Let us see if I got it right. I think I should. So, advection, right, the what do we say, speed of flow of that fluid times concentration, let us see, right, and diffusion minus, because it is due to concentration gradient from higher concentration to lower concentration, diffusion coefficient, which is a characteristic of both of the compound and the particular medium it is in. For example, we were talking about the scent bottle and the volatile compound, which gives you the smell. So, here the diffusion coefficient is going to be a property of both the volatile compound and the medium, which is air, let us see, right. Again diffusion coefficient and del product of concentration, let us see, with respect to diffusion, advection and diffusion. So, if I plug these in, what was the earlier equation? dC by dt plus del product of flux is equal to plus or minus sources or sinks. So, if I plug this into here, right, again as I mentioned, velocity of the flow of the fluid and diffusion coefficient, I discussed this. So, plugging this in, we will have advection on this side and diffusion on this side. And for surface water flow, let us say, typically because advection is so fast, or transport due to advection is so fast, we can typically neglect the diffusion term, and most of the aspects we are going to discuss in class, we are not going to look at it, but as we saw for the example of groundwater, where the groundwater flow velocity will be less, diffusion is remarkably important though. But for most other examples that we are going to look at least in this class, because advection is so fast, the mass flux there is going to be much higher compared to diffusion. That is why we are going to neglect diffusion, and I think that is what I have here. Considering flux due to diffusion to be negligible, in the case of surface waters, and considering the reactions that lead to formation or loss of compound, which is sources or sinks. I can simplify this further. This I am going to say is going to be 0, right, dC by dt plus del product of UC and rate of formation of the compound minus rate of loss of the compound. Again, what are the units of this, each particular term here? Again, concentration is mass per volume, and here we have time. Flux is mass per area per time. Again, del product, it is with respect to any dimension, right, dou by dou x. So, again that is where you get the volume here. Again, what this rate of formation, right, if you know Kc or rate, I guess Kc, right, again it is mass per volume, change in concentration with time, let us see, right. So, the units are mass per volume per time, let us see, for each set of variables here, right, rate of formation of the compound and rate of loss of the compound. So, again to simplify it further, if we took the case of the Ganga canal and the waste coming from Haridwar to Roorkee, right, what do we have out here? What do we say? We are only concerned with flow of fluid in the x direction and not in the y and z directions, let us say, right. We are only concerned with x and not y and not z, right. So, that is why instead of dou by dou x and y and z, we say that there is no change in concentration along y and z directions. So, that is 0, we are only concerned with dou by dou x. So, what do we have? So, with the del product, it will now transform into dC by dt plus u dC by dx. We are assuming obviously the flow is the velocity is constant here. Dou by dou x here we are approximating with dC by dx is equal to rate of formation minus rate of loss. So, this is the equation you will be using throughout this class, let us see, right. So, this is what I wanted to explain in this session. Again, we could have mugged it up, but I think it is always better to understand why you are what do we say, or how we came to this particular equation, let us see. Again, advection here, accumulation term here, rate of formation of the compound within your control volume, rate of loss of your compound within the control volume, right. So, what else do I have here? So, for macroscopic systems, again this equation can be applied for all systems, okay. So, it can be applied for systems where let us say concentration is changing at pretty rapid rate. But for example, if I want to apply it to this particular room, I am going to assume that the concentration of that compound within this room is the same, right. So, that is the one assumption obviously when we choose a control volume. So, if I am going to apply it for macroscopic equations, or not equations, pardon me, scenarios, the equation is slightly going to change, but it is going to be similar. So, accumulation term, mass coming in, mass going out plus source or sinks. So, what is it now? Again, volume of the control volume into dC by dt is equal to Q in C in, mass coming in, Q out C out, mass going out, plus volume into rate of formation minus rate of loss. So, what is it now? It is volume into concentration is mass per volume into time or divided by time, right. It is nothing but mass per time, and Qn or flow rate, rate of flow of your water coming into the reactor. What is it now? It is volume per time into what is Cn, it is nothing but concentration coming into the reactor. It is what is it now? Mass per volume, right. So, volume cancel out, mass per time. So, Q out similarly is the flow rate going out of the reactor, volume per time. C out is the concentration leaving the reactor. So, that is again mass per volume. So, again we end up with mass per time. So, here again volume into rate of formation, what is that? Obviously equal to mass per volume per time, right. So, again mass per time. So, here obviously all the terms are going to be mass per time, right. So, this is for macroscopic system. But again the equation that we had earlier, what was the equation that we had earlier? We had dC by dt plus u dC by dx is equal to rate of formation minus rate of loss. So, if you bring this term out here and simplify it for macroscopic systems, it is nothing but this particular system out here, right. So, I guess with that I am out of my time, but again please note that this mass balance we are going to use or at least I am going to ask you or try to ask you quite a few questions about this to keep your birds tickling now, right. So, otherwise everybody is going to doze off. So, again we are going to understand systems, again in practical systems we are not going to look at generic examples and such. So, you need to look at mass balance to understand how systems are going to behave. One example as I mentioned was, let us say Unnat Bharat Abhiyan, you will join these groups, or some of you might join this group, and they choose villages, I guess 5 villages, and recently one of the villages has been complaining a lot about their quality of water. Why is that? The industrial zone upstream has been discharging water, some of them treat it, some of them do not, that is the way of life. Typically they should treat it by law, but again we do not know who is not treating their water and discharging it, but over time the groundwater quality at this particular village has been affected. So, if somebody says prove that it is from this zone, or again I am presuming it is from the industrial zone, we can do it, let us say, right. Again you can apply this model, see how the mass is changing and where the source is, or you can try to estimate something or the source at particular industrial zone and then calculate the effect at this particular village, let us say, right. Again these are practical aspects, again if you want to do something practical and worthwhile. So, I guess that is what we are trying to discuss here, and I guess as I mentioned my time is up, and thank you for today.